So yeah, what I want to talk about is this topic towards AI for collaborative design and fabrication. So I'm going to try to show some of the things we are doing currently, some of the things we have been doing at the chair under this heading of collaborative design. Why is this AI topic relevant? Does this clicker work? No? Oops. This clicker. No? Yes. Okay. Yeah. Okay, so maybe some of you have seen this, right? So this is from Goldman Sachs, a sort of estimate all the tasks in white-collar industries that could be done by AI. And what's relevant for us here is that we have the office tasks, we have legal tasks, and then we immediately get architecture and engineering. So there is a really big challenge here, I think, where I have a whole talk about what this could mean for the profession. Today I'm going to talk more about our research and then maybe try to tie that a little bit back in. So what I want to talk about is some of you that are a bit familiar with computer science will know this is this pyramid. So we have data, but data is not the same as information. Information is not the same as knowledge. What we really want to have in design is knowledge. Most often we don't even have the data. So I will start with just showing a very basic data analytic projects from multi-actor fabrication. So that is this data category. Then the second step is this idea of surrogate modeling that you might be familiar with, that I will explain briefly, that I think is a really nice application in terms of these collaborative design applications. And then this was basically my PhD, surrogate-based optimization. So that is a little bit old, but I think that is still some information that I think I'm pretty sure some of you in this room will need to hear. Should hear. And then finally, this is my current obsession and knowledge graph for collaborative design, where I say this is the proper BIM for the 21st century. So, data analytics for multi-actor fabrication. This is a work by my PhD student, Leo. And so what Leo has done, he's basically built a sort of management framework for the various fabrication projects we undertake at the ICD. So what it does, it has a standardized data model in terms of describing various fabrication tasks that need to get done. It also has a schema that describes the various actors that could do these tasks. So it could be different robots, could be also humans. And then it sort of orchestrates the process where different actors step in at different times to do different things. So that is generally very useful, but of course then this, right, and so for example, here's the application where we do these very complicated robotically fabricated timber slabs, where we have a robotic platform here where you see there's, as I said, this kind of complex group of, we have two robots, we have a couple of people, we have a person with an AR helmet, and they all somehow need to work together. And so just as a very basic example, so what we then can do, of course, we can then data mine and sort of we can see what happens, and we can do a post hoc analysis, and so we can see the dominant time was taken up just in moving this table back and forth. And so the next step is now we also have a robotic table. So that's, of course, very basic. As I said, this is just about data and efficiency, but I think, yeah, I mean, I don't know many examples of this, right? So this is a very simple thing we could do in the construction industry to make things better, right? So first we basically we digitalize the process, and we know the process, and then we can somehow optimize it. And then, of course, the next step is we can do some sort of machine learning. So then we have a sort of regression model where then if I want to do yet another project, then I can start to predict how long this will take. Right? And that is also just something that's very useful to know. Like if I go with this kind of design, my robots are going to be running for this time doing these kinds of things. Okay, so this is one line of research that I could talk more about. Instead, I will talk about these surrogate models for collaborative design. So there, let's take a step back. But so surrogate models are essentially machine learning models that replace something that is expensive to evaluate, is how I would say it. So it might be like a very heavy finite element model that takes a long time to compute. Or in this case, of course, in this example before, my expensive data is I actually need to run this process to get this data. And so I replace it with a very lightweight machine learning model which replaces my function, and then I can get very rapid feedback. And so building simulation, I think, is very important. So here's my proof. So this is from the American Institute of Architects, where I think they give a very good example. By every year, they're collecting the energy improvement in the new buildings, like the operational energy. And they're basically saying, look, there are two factors that are driving the reduction in the operational energy. One is, of course, regulation, but the other one is building regulation, building simulation. So what we see here, there's a 10% gap. Just by simulating, you get a 10% improvement if you are in your energy efficiency. And it doesn't matter whether this was very optimal. It doesn't matter whether it was correct or not. It's more like this building simulation is like a thinking tool, which will lead to an improvement. And so, obviously, then it becomes interesting, okay, but these kinds of energy simulation models, they take a while. So here we have a basic model, and this is like a little work from my PhD student Max, who is also here, who will also teach the workshop on Friday, where, okay, so we do our energy simulation, heating, cooling demand takes 1 minute, which we think 1 minute is too slow for really collaborative design processes, and so we replace it with the surrogate. The surrogate takes 60 seconds. Okay, so that's very interesting, but the real key is that this then goes into a dashboard, and this is something we have done together with our engineering firm from Zurich, Gruner, where we have some kind of urban development in Zurich, and we can see all kinds of things that are interesting for a developer, like what kind of area do I have, how many parking spaces do I have, but I also see things like some sustainability criteria, embody CO2, and what we added to this, I also see now, okay, what will be the predicted energy loads, thermal, thermal loads. And so this is, to me, the real value of these computational methods. So it's not about finding optimal solutions, although this can be useful. It's also not necessarily, so it's not taking the human out of the loop. It's about making decisions more transparent. Right now, everybody can see it. Right, and so if we have a design briefing with a developer and the urban design authorities, we can just say, okay, so yes, there is a solution that has like a lot of volume and a lot of parking, but it scores very poorly on sustainability. On the other hand, we have a super sustainable solution, probably actually, as we hear this morning, building nothing is definitely the most sustainable. But then we can sort of negotiate and make better decisions. Okay. Then about this optimization topic. So as I said, this is what I did my PhD about. It's sort of close to my heart. So we've learned a little bit this idea, okay, I can interpolate an expensive function. Maybe I can use this to optimize. And that might be useful because maybe that's more efficient than, for example, the evolutionary algorithms that we heard a little bit about already today. And so my basic assumption is, okay, we all, of course, know what parametric design is. We should all do it, because then we can attach also quantitative performance criteria to our designs via simulations. And as I've argued, that's a really good way to go to more efficient buildings. And once you do that, you have also an optimization problem in terms of then it might be interesting to know what is the most performant design or the most performant designs that are possible, like in my parametric design. And so I always like to show this because this explains to me two basic facts about optimization. So here you see the optimization landscape on the top right, and there are these 3 little black dots. Those are the optima. And now the game is to find one of the 3. And we have a genetic algorithm, simulated annealing, particle swarm, direct and radial basis function optimization, so the surrogate-based approach. And so one thing you note immediately is some of these boxes have more black than others. So this means some algorithms have been more efficient. Right? So the game stops once you find the optimum. Therefore, if there's not a lot of black, it has been very efficient. So that's one thing. Right? So I have different strategies. Clearly, they have a different performance. The other thing you can see also, so these strategies are not only different in their performance, it's also different what they do. Right? So the genetic algorithm is a sort of quasi-random thing. It's very hard to see a pattern. In simulated annealing, you see that it's going in one direction, it's going in the other direction, it's going in the other direction. Particle swarm, clear, right? We see it's swarming. Direct is a dividing rectangle, also very clear. For architects, you always divide, and you keep subdividing until you have the optimum. And then ABF is this vague thing where it sort of randomly explores the space, and then it interpolates, and by interpolating, it very quickly can find the best point. So just another illustration of this. So in black, I have my true function. My dashed line is the surrogate. So you can see it's a very poor surrogate that is very far away from the actual function. If I now start adding points in, so Not great, but at this point, right now, it starts getting better. So I get a better fit to the function I want to model, and I also get closer to the low point, like the optimum. And so in this case, in like 5 steps, we find the optimum. Of course, this is very simple, but this was the basic principle. So basically, the basic principle here is I'm learning the underlying function. That's useful. That's also useful for the dashboard I showed you before. And at the meantime, I'm also finding the really good solutions. And so then what I did, I showed, okay, we can do this for structural optimization, we can do it for energy, we can do it for daylight. We get this as data, so we get a lot of different algorithms. Every algorithm gets 500 steps. You can see that the genetic algorithm, in this case, it's the Galapagos GA from Grasshopper, is absolutely the worst. So if you care about the performance of your building, that's just not a good approach, right? And then there's a lot of options that are in the middle, and then there is this machine learning algorithm here that is the best. Now I have to say that if you now have more time, right? Maybe your simulation is very quick. Maybe you say, okay, no problem, I can run 2,000 steps. Then one of the others, CMAES, is also going to be pretty good. CMES is just sort of what I call slow and steady. Now, this is, to my mind, like the closing argument. This is about the robustness. So now I repeat the experiment. And so you can see if you have a genetic algorithm, yes, basically it's random if you run it once. Yeah, most of the time it's good, but it could also be bad. And you have absolutely no way of knowing if what you get has anything to do with any idea of performance, right? It might just be a totally random result. And so basically what we need something that's over here, so something that's reliably gives not only good solutions, but also kind of, yeah, so good solutions and repeatedly good solutions, both if you repeat the same problem, but also across different problems. And so one special case is the direct algorithm here. Direct is deterministic, which means you run it on the same problem, you always get the same answer, but it still has a little error box because it works well on some problems, but not on other problems. So the algorithms on the left work well on repeated experiments on the same, but also across repeated problems. And we have Opossum in Grasshopper that you can download from Food for Rhino. You get RBF opt, you get CMAES. It's designed to, I know nothing about optimization. I press the button, it will give you reliable results. But as we feared, here obviously, so it's not really about optimization, right? So Opossum also gives you this performance explorer thing where we draw the whole fitness landscape. And because we say, well, in design, you're probably not going to choose the optimal thing, but you want to know what is happening, right? And so we have this visualization tool that tells you, yeah, if you go with options that look like this, that's probably pretty good. It's maybe not the best, but still in the world of fairly efficient solutions. And so this is also part of the newer versions of Opossum. I have to say, unfortunately, Opossum itself is not yet open source because it's internally a little bit of a mess, and I have only 2 minutes. And that's a real problem because we need to talk about knowledge graphs for collaborative design with symbolic AI for BIM. So symbolic knowledge graphs is when you type Paris into your browser and it says Paris is the capital of France and it has 7 million inhabitants and a site is the Eiffel Tower. I think that is the right way to do BIM. But this was always the dream. We've seen this morning, it doesn't work. You can make a living in 2022 repairing this problem. So this is still the reality, even though the paper is 15 years old. And so something is not working, right? A single BIM will never work. And so we think, okay, so this is our reality, this distributed. I move things between different tools. IFC says, no, let's have one single schema. Everybody can agree on it, but it just doesn't work. And so we hope, okay, maybe we can go in between. And so we agree on some things, but not on everything. And then let me just skip that. And basically, we think the solution is these kind of semantic graphs that capture the meaning, where I can capture the meaning from different disciplines, which are separate. So there's no need here to agree exactly on the schema. We just agree that we're going to model in this particular way with this particular type of graph. And we have based this whole thing on BOEM, an open source software from Biro Happold. So very pioneering, actually a company in the AEC that says, here's our data model, we make it open for everybody. And then what we did, we converted it into a graph, and then we built like a little software. So this is like a very first proof of concept where you can actually model like you would typically model, and then we generate the graph, and then you can look at the graph in GraphDB. And so the idea is basically you can model in a conventional way, and at the same time you get the graph representation, and the graph representation has all kinds of beautiful advantages. For example, you can make these very complicated queries that allow you to query your data. This is also one of the problems why this is not more popular, because you need a lot of knowledge to properly query your graph. So this is, but I think so we have solved the first problem, how you actually model something in this graph format. Now comes the second problem, how do I make these queries simpler? And with that, I'm going to close. So the future of construction is not automation, right? It's a collaboration between humans, computers, and robots, and I think this is not a new message. I think a lot of people have said this today. And so, and that's because the computers and the robots, they don't have this intentionality. Like everything I've shown you, still the human is somehow in the driving seat, right? And I can have support systems, but if there is a computer and a robot just sitting there by itself, it's not going to do anything. And so for me, basically, computational methods and specifically AI is what I would informally call the glue. So that's what you need, basically, AI to make this happen if you want to have humans and robots play together and if you want to design together. And that's what I'm looking forward to discuss with you as well as my other panelists.